Hello everybody and welcome back to our Artificial Intelligence course for biotechnology. So far we have learned what is machine learning and we looked at first classification models like the k-nearest neighbor classifier to do basic classification tasks. We have learned how we can evaluate our classifiers using common metrics like the accuracy, the specificity and the sensitivity, and we have learned how we can select the best model using cross-validation or train, test and validation splits. In this lecture now, we will look at linear regression. And some of you might remember linear regression from your statistics course. We will now look at a slight different motivation behind the linear regression model. But usually the connection between statistics and machine learning is usually quite close. So we use very much concepts that are coming from statistics and vice versa. The main difference, which we could summarize, is in statistics we use linear regression on the full data set to get a description of the data set. And in machine learning, we use parts of the data to train a predictive model that we then can use to do predictions on unknown data. And therefore, we have to compute or to estimate the generalization abilities of our model as we have learned it in our last lecture. So now let's start with linear regression. So what is linear regression? Linear regression is a linear model. And the family of linear models is quite huge. And in this lecture, we will start to learn what is a univariate linear regression to motivate all our examples. The nice thing about univariate linear regression is that we can visualize the data quite easily, and then it's easy for our understanding. We will then look at loss functions and what is empirical risk minimization and what types of loss functions are out there for linear regression. So let's go back to one of the examples that we have looked at in one of our first lectures. So we said a regression task is when we like to predict a continuous variable y. So in this example, we have, for example, all the different points are houses for which we know the flat size. So the feature is our flat size and we like to predict the price in dollar. So what we like to do here is we like to find a decision function or a linear function that describes our data as best as possible, and that we can use this linear function then to predict if we have a new flat for which we only know the size, that we can predict the price of this new instance. So to summarize this, the goal in regression is that we like to predict a continuous target variable y, which is in statistics called the response variable, by a linear transformation of our single feature x1. And that's called usually the explanatory variable. So what do we need here for? We said we like to more or less compute here a linear function that describes our data as best as possible. And you might remember from math that the linear function is defined as the following. So our y is a linear function which is defined as beta 0 plus beta 1 times x1. And in machine learning, we here usually use Greek letters. So beta 0 is nothing else than our intercept on the y-axis. Or we usually call this also the bias or the error term. Beta 1 is nothing else than the slope of our linear function. You might remember this. So the slope is the delta of y divided by the delta of x. So that's in a statistical model or in a regression model called the weight coefficient. So we have here a bias and we have a weight coefficient. And that defines our linear function. So now I'd like to define what the hypothesis space H is. Therefore, we use this hieroglyphical letter H. And the hypothesis space is the set of all possible linear functions in our coefficients beta. So the problem is, we actually would like to find this line here. But if in the case when we only have all these data points here, we usually don't know what is the best linear function. So is this the best linear function? Or is this the best linear function? Or is this the best linear function? Or which of these all linear functions that we can create here with a beta 0 and a beta 1 is the best linear function that describes our labeled data as best as possible? So what are the optimal parameters beta 0 and beta 1? That's the question we like to find out. So we have to find here this linear function that describes the data, this underlying data, as best as possible. And therefore, we have to define the loss function. So the loss function, which is usually also called in some cases the cost function or the risk, is a non-negative function that measures the disagreement between its argument, which means it measures actually nothing else than the quality of our prediction y hat. And how can we measure the quality of a prediction? We quantify how close is our prediction to our original variable y. That's a loss function. So here we also use the graphical letter L, and this function, this loss function L, takes two arguments. It takes the true label and it takes here f of x. So the prediction, so f of x is computing the prediction of our data point for a given beta 0 and beta 1. So we can quantify with a loss function the quality or the disagreement between our prediction and our true label. The empirical risk is then the average loss of the model f for a given dataset D. So the loss function is computed for a single instance. So we have one y and we have one prediction, then we can measure the disagreement between those 2 points. The empirical risk then averages all the losses for all the samples in our dataset. So for example, let's say we have 100 instances, so 100 houses, and then we can measure the prediction of our 100 houses, compare it to the true predictions, which gives us the loss, then we sum it all up and divide it by the number of instances. So it's nothing else than the average. That's called the empirical risk. And our goal is now that we minimize this empirical risk. And this is called empirical risk minimization. So the learning of our model is finding the smallest average loss, which is nothing else than finding the best model. So the best model, which I donate here again with the hat, f hat, is the argmin of our empirical risk, which is the linear function out of our hypothesis space H that describes the model the best. So first, let's look at some loss functions. How can we measure or quantify the quality of our predictions? And therefore, we look at first at the so-called L1 loss or at the absolute error. So let's say we have here again our feature x1, which is, for example, the size of the house, and we have our target, which is the price of the house, and then we have here a linear function. So we have one set of beta zeros and beta 1s, and then what we can do is that we can, when we have here a prediction, that we measure here the absolute error of the true label to the prediction, which is nothing else than y minus y hat, and the absolute value of it. That's the absolute error. Quite easy. This we compute here for all the samples in our dataset. And this gives us the loss of our linear function compared to our data points. So here I plotted the loss again. So at the y-axis you can see the loss for a given variable y and the prediction, and here we can see the residuals. So y minus the prediction is also called the residual, and you see that when the prediction here, so the prediction is equal here to our y, then here the loss is 0. Of course, when we have done everything correctly, then we have no error, so the loss or the error is 0. When we do somehow errors, for example, here our prediction is smaller or larger than our true value, then we are somewhere here on the line or somewhere here on the line. If we take the absolute value, it gives us the distance from this point, for example, to this point. And that's the error that we made. So the goal is, as I said before, that we like to find the beta values that minimize this L1 loss. So we like to minimize the absolute errors that our line makes, so our linear function makes, when we put it here into the graph. So we like to find now these beta values, this beta 0, which is here, somewhere the intercept, and the slope that minimizes the error, the absolute error between our linear function here and our data points. So now let's look at the surface of this L1 loss. So I used Python here to plot the surface for all beta 0 and beta 1 values in a specific range. So I said the intercept, so beta 0 can be between -4 and +4, and beta 1, the slope, can be between -4 and +4. And here on the z-axis you can see the L1 loss. And that's the following surface in the three-dimensional space. So what we actually like to achieve here is we like to find this beta 0 value and this beta 1 value that leads to this minimal loss. And where is the minimal loss? The minimal loss is here in the valley of this function. So when we are somewhere here on the borders, we like to go down the gradient until we reach the minimum of the function. That's the beta values that lead to the minimal loss. However, there's one problem with this absolute error. There is no analytical solution to compute the betas. Why is this the case? As you might remember from mathematics, there is no derivative for the absolute value when the prediction is equal to the true label. So if y is equal to the true label, then both are 0. So then we must compute the gradient at the point 0, which is not possible. So there is no analytical solution how we can compute this. So what else could we do? We could, for example, compute the L2 loss. The L2 loss is nothing else than the squared error. So instead of computing here the absolute error, we now compute the squared error, which is nothing else than y minus y hat squared. So we just square up the errors, which I visualized here. So we not only have here the distance between the point and the linear function, we now have here a square. So we square up the errors, which is then nothing else. So the prediction I said is f of x, that you know from before. Our linear function gives our prediction, and the linear function is defined as beta 0 plus beta 1 times x1, and then we square the difference between the true and the prediction. So here I visualize the loss function again. And the nice thing about this loss function is that's a parabola. And you know that when we compute the derivative of a parabola, so for example x squared, it always has a derivative. So x squared has the derivative 2 times x. So again, here the goal is the same as before. We like to find the beta values that minimize now this L2 loss. So what's that? That's our estimated betas. So the betas we would like to find is the argmin of here the risk minimization. So the average, the empirical risk, the average loss between our prediction y here and the true label. We square it up, we sum it up, we divide it by n, and therefore we like to find those values that lead here to the minimal value. One problem with this L2 loss is, compared to the L1 loss, that if we make, or if the errors are rather large, we might get an even worse error when we square it. So now let's look here at the surface again. This is the surface of the L2 loss. So here again we have the beta 0 and the beta 1, so different beta values, and I plotted all the possible losses for these beta values. That's the surface. And again now we have to find here the gradient that leads here to the minimal point, which then leads to the optimal beta 0 and beta 1 value. So again, minimizing the sum of squared errors is computationally much simpler than minimizing the L1 loss, because we can compute derivatives. So let's look at an intuition again. I said that the goal is that we want to find these beta values in our linear regression model, that we can find a linear function that leads to the minimal empirical risk. And that's exactly then the linear function out of our hypothesis space H that fits the data optimally. So now let's take a toy example. We have here a few data points. So all of this stuff is generated in Python. And if you're interested in to see how I generated this data and how I generated these plots, I uploaded here a Jupyter notebook, which you can download from the website. It's optional, just for your references, that you can look up how I computed, for example, these plots and so on. So let's go back to this example. I said I had here different data points. And I now take the L2 loss with different beta values. I just randomly pick some beta values. So let's say in this example, I randomly pick for the intercept 3. So the intercept here with the x-axis at point 0 is 3. And it should have a slope of 3. So it's a rather steep line, linear line. And then we compute all the squared errors from the points to our linear function here. And you see that, of course, the L2 loss is rather large with 170, because our errors are rather large. Now let's take some other random beta values. If we now say, okay, our beta 0, so our intercept should be at 0, which is here, and it should have a slope of 0.1, so very flat. Then we can compute again the L2 loss, so we compute the squared error from this point to the line, from this point to the line, from this point to the line, and so on, and then we sum it up, and then the L2 loss is here much smaller now than compared to this example, but we see, yeah, it's still rather bad, because this line does not really describe the data in our plot here. So let's pick some other beta values. Let's say beta 0, so our intercept is at 1, and our beta 1, so the slope is around 0.9. Then the loss here gets even more minimal, it's only 2.28. So our errors are rather small, and this we can see here, the squares which are plotted here are much smaller now than in these two images. But the question is still, have we already found the beta values that describe the best possible line? No. There is another combination of beta values. So here, for example, beta 0, 0.6, and beta 1 is 0.8, which describes this following line here. It very much looks very similar to this plot here, but it's still a little bit different, so it's a little bit shifted here, and this leads to a minimal loss of 1.87. And here on the right hand side you see the error surface for all the beta values now which we tried out. So here we have the beta 0, here we have beta 1, and here we have the sum of squared errors, so the L2 loss. And you see here the orange plot, this was this one here, this was rather high in the plot, so it was not really at the minimum. And then you see that we came here closer to the minimum. So this plot here had already a much smaller L2 loss, but it was still rather high, not really at the minimum. Then with this plot, we jumped here into the valley, and the green plot is here. That's this point, which are the optimal values in this valley. So these are the point in the valley that has the minimum value. And now the question is, how can we find now these optimal beta values? We said we have to do empirical risk minimization, so we have to find the minimum, but how can we find the minimum? How can we find the optimal beta values that lead to the minimal average loss? And that we can do when we use a L2 loss by computing more or less the gradients, and therefore we can also compute the derivatives. So finding the minimum here of this function is, when you remember in math, when we have a parabola, finding the minimum of a parabola, therefore we have to compute the first derivative, and then we have to set it to 0, that we then can say, okay, at this point we have the minimum value. And this we now can also do in matrix notation or with linear algebra. And we will go through these derivatives now. So we will do now a regression with L2 loss. And that's the usual linear regression model you know from statistics. It's also called the least squares method. And the nice thing about this L2 loss is that it has an analytical solution. So we can compute it actually. So what we have to do is, we have to solve this minimization problem here. So we like to find the beta values that are minimal for the L2 loss. And therefore, before we do this, we first integrate here this beta 0 into a vector. So we now say the bias beta 0 is now integrated into a vector which we call beta. So you see it's bold, it's a vector which contains beta 0 and beta 1, and is transposed. And we also include a column of 1s into our design matrix X. So X is our data matrix, which you might know before. So we have here only one feature, which was, for example, in our case, the price of the house for n different samples. And the first column here is just a column out of 1s. And what does this allow us? This allows us that we can rewrite this sum here, beta 0 plus beta 1 times x1, in matrix notation. We now can write that this is nothing else than 1 divided by n, the sum of I equals to 1 up to n. So over all our samples, we now compute here the error between our true label y and our prediction, which is here to make it as beta transposed times x for the sample I. Then we square it, we sum it up. And this form might be familiar to you again, because this looks very similar than the Euclidean distance. So if we put here a square root around it, then it would be at the Euclidean distance. So we can rewrite this sum here again in matrix notation. So this is nothing else than the minimum of 1 divided by n, and then we have here the notation for the L2 norm, and then we square the L2 norm, that the square root disappears again, and then this is nothing else than the vector y. So all our true labels minus all our predictions, and this is squared up, and then this we have to now minimize. If you can't remember some of the linear algebra things here, we recommend to you the following book, which you can find here under this URL. That's a book for mathematics, which is important for machine learning. It's a comprehensive book, but it also has some details that help you to refresh your linear algebra skills. It's open and you can download it for free under this URL. So I now said we have to minimize this function here that we can find the optimal beta values. So how do we do this? We first rewrite here this function using some identities which we might know or still know from linear algebra. So one identity is that if we have A plus B transposed, that this is nothing else than A transposed plus B transposed, and that A times B transposed is nothing else than B transposed times A transposed. So now here the matrices are switched when we transpose here the multiplication. And this we can use then to rewrite our equations. So this was the Euclidean norm, the squared Euclidean norm, or the L2 norm, and then the squared L2 norm, and this we can rewrite as y minus x times beta transposed times y minus x times beta. That's equal to this. And then we try to get this transposed into the parentheses here, which we can use by following these identities. So that's then nothing else than y transposed minus beta transposed times x transposed, and then times the in parentheses y minus x times beta. And this we have to minimize. And how do we find the minimum of this function? By computing the gradient or the first derivative. And that's what we do next. We compute the derivative with respect to beta, because we like to find those beta values that lead to the minimal function here. So we rewrite here this expression by multiplying it. So y transpose times y minus y transpose minus y transpose times x times beta, so minus y transpose times x times beta minus beta transpose times x transpose times y plus beta transposed times x transposed times x times beta. So we just used multiplication to remove the parentheses here. That's what we have here. And now we have to compute the derivative for this function with respect to beta. And therefore we might use again some useful identities. So the derivative of ax with respect to x is nothing else than, or is the same than a transposed times x, which is the same of the derivative of x transposed times a, which is a. That's the same which we know from basic calculus. And another useful identity is when we compute the derivative with respect to x of x transposed a times x, then this is nothing else than 2 times a times x in the case if a is symmetric. So let's now do the derivative here. So what we get here is then, after we simplify this, so this is simplified nothing else than y transposed y minus 2 times beta transposed times x transposed times y plus the rest here, beta transposed times x transposed times x times beta. And then we compute the derivative. So here we don't have a beta, so this is 0. Here we have 1 beta transposed, so this is then nothing else as 2 times x transposed times y. And then we have to compute the derivative from this term here, beta transposed we have here and beta here, so we can use here this identity, which is then nothing else than 2 times x transposed t times x times beta. So we computed now the derivative, and now the last step what we have to do is to find the optimal betas. We have to set it to 0. So we set it to 0, and then we solve for beta, and then we know the formula for beta when it's minimum. So we can compute this, we set it to 0, and then we say, okay, this is then nothing else than minus 2 times x transpose times y plus 2 times x transpose times x times beta. So the 1 divided by n just disappears because we have here 0. Then the 2's will disappear, and then this is then nothing else than x transposed times x times beta is equals to x transposed times y, and then if we solve for beta, then we get the solution. So the estimates of our beta are then nothing else than x transposed times x, the inverse of it times x transposed times y. So that's the estimates of our linear regression. So that's a lot of stuff we have done here, and then we get this nice simple formula, and that's all we need to compute a linear regression. So we have a nice closed form solution for this. And now let's put it all together. So what do we need for a linear regression with the L2 loss? Of course, we need some labeled data. Then we need our hypothesis class, which in our case is a linear function. So the linear function is defined f of x is nothing else than x times beta. Then we need our L2 loss. The L2 loss we have defined before. And we need our beta estimates to that we can compute the optimal betas, which is nothing else than this formula here, which we just derived before. So what we have to do is we take our training data, we compute this small equation here, and then we already have our betas, and then we can use this estimated betas to fit a linear regression model, and then we can predict on new data points. That's all we have to do. The question is now, could we also use the L1 loss for linear regression? Because I said before, we have the problem that we can't really compute the gradient for the absolute value of a function, in the case if the absolute value is 0. But we still compute, or we still could use the L1 loss for linear regression. However, it's much harder to optimize. There's no analytical solution, as I said before. There's no derivative, and the gradient is always 1. So we always make the same steps down the slope. We can solve this by using numerical solvers, like for example conjugate gradient or others, but this will be not part of the course, how we can do these optimizations. Therefore, we recommend other courses at this campus where you learn about optimization techniques. One big advantage of the L1 loss compared to the L2 loss is that it's way more or less, let's say like this, it's less sensitive to outliers in our data. So let's look at an example. If we have no outliers in our data, like in this example, then the L1 loss and the L2 loss here are quite close to each other, and the lines or the linear regression or the linear functions we found are rather similar. However, in the case if we have an outlier, let's say this point here is not below here, it's up here, then the L2 loss would lead to the following linear function. So we have here the squares, and this linear function leads to the minimum error using the L2 loss. However, if we would use the L1 loss, then we see that we will get the following linear function. So we don't consider here this error as important as when we do it with the L2 regression or the L2 loss. And the reason for this is, in the L2 loss, the square of the error is much larger and much more important than if we only would look at the absolute difference. So using the L1 loss helps if you have a lot of outliers in your data to still find a good model for your prediction task. So now we looked at this univariate linear regression, which means we have only one feature x, like the size of the house. But usually in real-world machine learning applications, when we work with biological data, we have hundreds or even thousands of these features. We might have thousands of positions in the genome for different individuals that might differ, or we might have several measurements for a protein, or in this house example, we might have not only the size of the house, but we also might have how many windows does the house have, how many doors does the house have, how many floors, and so on. So we might have more information that helps us to predict the true target variable y. And that's then called multiple linear regression. So we have multiple features. The question is now, how can we use this framework that we looked at using multiple features? And the good answer is we don't have to do anything else. The nice thing about linear algebra is that we have everything in vector and matrix notation, and we just could here in X create more features or add more features to X and add for each of the features a beta value, and then we can do exactly, or we can use exactly the same formulas to compute or to estimate these beta values. That's a very nice property. So one last thing I'd like to discuss with you now is how can we evaluate regression models? How can we evaluate on test data how well our regression models perform? And that's the last few slides I will go through in this lecture. So one is the mean squared error. That's actually nothing else than the L2 loss. We use, when we, for example, use the L2 loss to optimize our model, we can use the mean squared error in the end on the test data to check how good are our predictions on the test data compared to the true labels we have in our test data set. However, when using the mean squared error, we have to pay attention to that the predictions with a large error might heavily influence the mean squared error, because, as I already said before, they add up quadratically. Here, instead of the mean squared error, we also use quite often the sum of squared errors, which is nothing else than we just remove here this 1 divided by n, so we don't normalize it, it's then just the sum of squared errors. Or sometimes we also use the root mean squared error, which is then nothing else than putting around the square root, which helps us to bring back the measures to the original scale. Because if we square them here, the error looks quite large, and if we use here the square, we can transform them back to our original scale. Another measurement that's very often used is, of course, then also the mean absolute error. So when we optimize with the L1 loss, we could also compute the mean absolute error on our test data. However, it's also possible, for example, that we fit or estimate our beta values using the L2 loss on the training data, and then on the test data we use the mean absolute error. That's absolutely possible. So we always have to distinguish between how we optimize the model using the loss for the optimization, for the finding of the beta values, and then there is the measurements that we then use to evaluate our model, so the scoring of our model. These are, in this case, very often very similar measures, but we have to distinguish between the training, so the estimating of the betas, and the testing. And the last measure I would like to show you is the coefficient of determination, which you still might know from statistics. So capital R squared is then nothing else than 1 minus here the sum of squared errors divided by the sum of squared errors, but here we don't use the prediction, here we use the mean of all our y values. So what do we do here? Here we compare the sum of squared errors of a model that performs like the average or like a baseline to the model on our predictions here on the more complex model. So if r squared is equals to 1, then we have a perfect prediction. We don't do any errors, we have a perfect regression model. If r squared is equal to 0, then we know that our predictions are as bad as the baseline model here. And what does it mean? We just do predictions as good as just computing the mean of our y values. So if we compute the mean of our y values, we will get exactly the same performance than if we would use this model that leads to r squared is equals to 0. And here it's also possible that we get negative values, and it can go down to minus infinity. So negative values might indicate overfitting, because then we learned a model that performs worse than the model a model that just uses the mean for the predictions. But also a model can be overfitted even if r squared is larger than 0. This we will see in an example later. And very often the r square measures is also used to compute more or less the fraction of the variance explained. So we can say when we have a y value here, we have some y's, and then we can use the r square measure to say how much of the variance in our data, in our target data, can we explain by our predictions. And that brings me already to the end of this lecture. So what should I know and what should we know? We should know what is a linear model. We should know all the building blocks of a linear model and what a loss function is. So what's the difference between the L1 loss and the L2 loss? What is empirical risk minimization, or what do I mean with the word empirical risk minimization? And we should know how to estimate the unknown beta. So in our case, we should know it for the L2 regression. And we should know the difference between a univariate and a multiple linear regression, and how we can compute the performance, or how can we measure the performance of our fitted regression model. That brings me to the end. I will upload also a hands-on video where we will try out the linear regression using scikit-learn and a toy dataset. Thanks.